Okay, so now we're going to talk about two uses for dot product. The first one is going to be projection. Now think of a projection as kind of like a shadow. Okay, so if you're walking along and take a look at your shadow, you are basically projecting yourself onto the ground. Okay, so here's you. Forgive the artwork. Here's the ground. Okay, sun's coming down, and we're projecting your shadow onto the ground. Okay, and what happens is, whatever we're projecting to, we're going to create a 90-degree angle. Okay, this is a really bad picture. Okay, so if we project a vector, we'll call it A, onto another vector, we'll call that B. Okay, we're going to get a diagram that looks like this. Okay, so there's the vector A. There's my vector B, sorry. Okay, now I'm going to project A onto B, and it's going to make a 90-degree angle. Okay, okay. The notation is A sub B. So this literally means the projection of vector A onto vector B. Okay, please note that the length or magnitude of the original vector A is not necessarily the angle, or excuse me, the magnitude or length of the projection. Just like your shadow isn't the same height as you, okay? Sometimes your shadow is really short, other times your shadow is really long, other times it's the exact same height. So, same type of thing. The projection is not the same magnitude as the original, okay? All right, so here is our formula. The dot product of A times B is equal to the magnitude of B times the projection of A onto B. Okay? So let's try that out. Okay, it's kind of a confusing formula because you're just not used to it. Okay, so I'm going to do a problem that's just basically directly from the assignment. Okay? All right, so we have the vectors of A and B. So A is 21, B is 44. Okay, and the cosine of the angle between is 7 over 12. Okay, so we want to find the scalar projection of A onto B, and A dot B. So we want to find A sub B. Okay, and then we want to find the dot product. Okay, so here we go. So we have two formulas working for us. We have A dot B is equal to, excuse me, got that. Okay, and then we have our new guy. Okay, so this is a little weird because this question kind of asks you things in the reverse order in which you need to find them. Okay, so you actually need to find A dot B first, and then you can find the scalar projection of A onto B. Okay, so here we go. We're going to use this formula first and this formula second. So A dot B is 21 times 44, magnitude times the magnitude, and cosine of theta is given as 7 over 12. So we can just kind of pop that in. Okay, and then we're going to use our calculator. And we get 539. Okay, so that's A dot B. Now we can take the dot product that we just found. Okay, B is equal to 44, and then the scalar projection of A onto B. So we're going to divide. And then we get 12.25. There we go. That's it. Okay. All right. So not too bad. Now let's talk about work. Okay, work is the transfer of energy from one place to another. Okay, we talk about force, and then we talk about displacement. Okay. All right, so work is going to be the magnitude of the force times the magnitude of the displacement. Okay. Now, this is if we're using the same direction, not in different directions. That's a little bit more complicated. Okay. Now, if the direction is different, then we use this formula. Okay. All right, so let's do some work. All right. Find the amount of work if we have a force with a vector of 2, 10, but our displacement is given by points. So our initial position is 3, 2. Our final position is 10, 15. Okay, so to find our displacement vector, just go final minus initial. So 10 minus 3, 15 minus 2. Oops. So 7 and 13. Okay, so everything's moving in the same direction. So to find our work, we need the magnitude of the force times the magnitude of the displacement. Okay, let's find those. So that would be 104. And then $218. Okay. So my work value is the square root of 104 times the square root of 218. Take the square root of that. 150.57 units of work. Okay, now work is generally in things like joules, or another one is, I want to say foot pounds. Okay. All right. So let's do another example where our directions are different. Okay. Okay. So we have a tow line. Okay. And then the angle between is 30 degrees. Okay. So our force is going to be 50 newtons. And our displacement is 7,000 meters. So we have a work equation. Okay, this one looks harder than it is. So we simply just plug everything in. So 50 times 7,000 times cosine 30. And this would be in joules because it's in newtons and meters. Okay, or in Ingenuity, they round. And there we go. That's it. An interesting fact is a joule is also used for like a calorie too. They're connected. So sometimes if you look on the back of food packages from not the United States, you'll notice that they give the energy level like kilojoules. So kind of the same thing. All right. So thank you for listening, and I hope that wasn't too painful. All right. See you.